So the tricks that we are doing, that we're going to look at, come from this book, Magical Mathematics, which I'll pass around at some point. Someone gave this to me this summer, and I started reading it, and it's really interesting. I have not gotten that far into it, but just in the first couple chapters, there's a lot of really cool math in here. Some of it is pretty easy to follow, and some of it is, I still haven't figured it out yet. I'm still looking into it. So there's a lot of great topics in here. So I'll pass this around at some point so you can take a look at it. What we're going to do is look at 3 different magic tricks, and the first 2 are kind of related. So I'm going to demonstrate the tricks, and then I'll talk about the math behind them, and then the third one kind of has some open-ended stuff, so I'll kind of tell you what I've been looking at, and then it might invite you to ask some questions. I don't have enough cards for everyone, but most of you should have a pack of 4 cards in front of you. If you don't, see if you can find someone near you that you can share with. There's a few things you'll need to know for these tricks. So the first thing is what a shuffle is. So shuffle, which sometimes is called a riffle shuffle, is kind of the standard shuffle. So you're just mixing them all up together, which is hard to do without a table. Here we go. Mixing them up that way, or some people like to, I can't do it, but you mix them up this way. So that's a riffle shuffle or just a shuffle. The next thing you need to know is what a cut is. So a cut, you're just taking some of the cards off the top, or none of the cards, but usually you take some. It could just be one, could be a lot of cards, and you're going to take them and you're just going to put them on the bottom. So if you want to practice with your cards, you can. So you're just going to take some from the top and put them on the bottom. So that's a cut. And then the next thing is a little more complicated. This is called a Hummer shuffle. So a Hummer shuffle is first a cut. So you cut, and then you take the top 2 cards. So cut, you put them on the bottom. And then you take the top 2 cards and you flip them over and put them on the top. Now, if you do a couple of these together, it's going to mix your cards up quite a bit, and some will be face up and some will be face down. So if you do it again, if you cut, and then you take your top 2 cards and turn them over, that's a Hummer shuffle. So do it as many times as you want. You can cut, turn the top 2 over, cut, turn the top 2 over, and so on. So we've got a riffle shuffle, where you're just mixing the cards up. You've got the cut. You just take them from the top and put them on the bottom. And then the Hummer shuffle, where you do a cut and then flip the top 2. Are you okay with those? Yeah? Okay. So I'm going to ask for volunteers throughout this. So make sure you know how to do these, because I might be asking you to do them. Now, this first trick, everyone who's got cards can do. So what I'd like you to do is take your cards. You're going to put them in a pile. So they're all facing the same way. And it doesn't matter which cards you have. That's not important. Then you're going to look at the card that you have on the bottom. So take your pile, look at the card on the bottom, and you want to remember that. So that is your card. Okay, so now what you're going to do is take your top card, and you're going to put it on the bottom. Your new top card you're going to take and you're going to flip over. Now you're going to do the Hummer shuffle as many times as you want. So remember, the Hummer shuffle is a cut, and then you're going to flip 2 cards. So cut your cards, flip 2, cut your cards, flip 2, cut, flip 2. Do it however many times you want, but like at least 5 or 6 to make sure they're really mixed up. All right. Now, the next thing you're going to do is take your top card. You're going to flip it over and put it on the bottom. Your next card you're going to take and just put on the bottom, but don't flip it. And the next card you're going to take and you're going to flip over so it's facing you, but keep it on the top. And now in a second, you're going to spread your cards, and 3 of your cards are going to be facing one direction, and 1 is going to be facing the other direction. And the one that's facing the other direction, what do you think you're going to find? It's going to be your card, right? So raise your hand if you got it to work, if you got your card. Okay, all right, so maybe with the shuffling, if you put some cards in the wrong order, then maybe it didn't work. But that trick is called the baby hummer. That was the baby hummer. So look how many people it worked for, right? And you all shuffled differently, right? You cut at different points, flipped 2 over, but your cuts were different every time. And you were still able to get your card to show up. That's the baby hummer. We're going to talk about how it works in a second. But now I want to show you the royal hummer. So I need a volunteer to come up and help me with this one. Come on up. Can you tell us what your name is?
My name is Carolyn.
Carolyn. Okay, Carolyn is going to shuffle these cards. I'll show you what I have first. So these are the cards we've got. It's not the whole deck. It's just some cards. But you can see what's in there. Carolyn, you're going to shuffle these. So shuffle them a couple times. Yeah, it is.
Oh, go ahead.
Full deck to do that. Or maybe she's not playing with the phone.
Yeah.
All right. Okay, so Carolyn's mixed them up. You can see what we have. So she mixed up the order. Now what I'm going to do is I'm going to mix them up so that some are facing up and some are facing down. So kind of like half and half, facing up and down, you can kind of see. And if I flip it over, half are up, half are down. So Carolyn, come on over here. I'm going to take 2 cards at a time, and Carolyn is going to tell me whether I'm going to flip them, turn them over, or not flip them. So flip or don't flip.
Flip. Don't flip. Don't flip. Don't flip. Flip. Don't flip. Don't flip. Flip.
Okay. Now we're going to do this one more time, but with 4 at a time. So again, flip or don't flip.
Don't flip. 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 Don't flip.
All right. Should we do it one more time? Let's okay, we'll do 2 at a time again. So flip or don't flip.
Flip. Flip. Don't flip. Don't flip. Don't flip. Don't flip. Flip.
All right. Okay. Now, what I'm going to do is separate it into 2 piles. So I'm going to make 2 piles. Now, the next thing I'm going to have Carolyn do is take one of these piles and flip it and turn it over onto the other one. But before I do that, I want to ask you a question. In poker, what is the best hand that you can get in poker? A royal flush. What's in a royal flush? 10, jack, queen, king, ace, all of the same suit. Good. So Carolyn, take one of these, and you're either going to flip this over onto this pile or this one onto this pile. Good. Okay. So now let's see. What do we have? Yeah, I'll do it here so you can see. We've got the royal flush, right? That's true. That's true. Good. That's the royal hummer. Good. Thank you, Carolyn. Okay. So now the question is, how does this work? Does anyone think they know how it works? No? Okay. Both of these tricks have to do with the idea of parity. So parity is the idea that we've got even numbers and we've got odd numbers. And if you look at all your numbers starting with 0, 1, 2, 3, 4, and so on, all of those are either even or they're odd. So if I take the cards that I have, what I did in the process of shifting the cards around is I kind of split them into the ones that were in an even position and an odd position. And at some point, I kind of intervened in the process to make the royal flush card stand out. So what I'm going to do now is show you the trick without my intervention, so you can kind of see what the pattern is, and then I'll show you what I did to make the royal flush card stand out from the rest. So Carolyn shuffled, so it doesn't really matter what order we have the cards in. And then the next step was for me to mix the cards up so some are facing up and some are facing down. So our default here is that any card that is in an odd position, so that would be the first card, the third card, the fifth card, and so on, those are all going to be facing up. And all the even positions, so the second position, the fourth position, the sixth position, those are all going to be facing down. So when I take my card, so this is the first card, so that faces up. The second card faces down. The first card faces up, and so on. So I'm just putting them like this. And so we can kind of keep track of what's going on. I'm going to write this on the board. So 1 is going to stand for an odd position, and 0 is going to be if we have a card in an even position. So now, after I've mixed them up, the order of my cards looks something like this. So again, 1 is odd position, and it's facing up. And 0 is an even position. And it's face down. So again, this is without me doing anything to change the order. So we have every other card here. Now the next part of the trick was to take 2 cards at a time and either flip them or don't flip them. So the first 2 cards, for example, would be these. So that would be these guys. Now, if I don't flip them, it doesn't change anything, right? The first card is still 1, the second card is still 0, and the numbers are preserved based on the position that they're in. If, however, Carolyn had told me to flip these, what would happen? Well, the first card is face down. Actually, let me I'll do this. It doesn't matter whether we're up or down. So the first card is face up, and the second one is face down, right? If Carolyn had asked me to flip them, what would happen?
Still first card is up.
Still the first one is up, and the second one is down, right? So the particular card that we're talking about, so here the 10 of spades is the first one, and the 10 of clubs is the second one. It changed, the position in the set of 16 cards changed, but the direction it was facing was still preserved. So in fact, if I take 2 cards at a time, if I flip them, I still am going to get a 1 and a 0 here. Does that make sense? And in fact, if I take 4 cards at a time, if I don't flip them, nothing changes. If I do flip them, in terms of parity, nothing changes also, right? Because I have up, down, and if I flip, I still have up, down. So in fact, you could think of this action of flipping, if I have an even number of cards and I flip, this is kind of like an identity operation. So for those of you who have taken an algebra class and you've talked about an additive identity, who knows what the additive identity is? What number can I add to anything and it doesn't change it? 0, good. What's the multiplicative identity? 1. I can multiply 1 by anything and it doesn't change it. They're identities, right? It doesn't change what's going on. It preserves the state that we have. These flips are like identity operations. So I can flip and it doesn't change the parity situation that I have going on here. All right. What was the next thing I did? After the flips happened, I separated them into one pile and another pile. Now, if the parity is preserved, I did every other one, right? So my first pile should be all face up or down? Yeah, it should all be face up, right? Because if I'm doing 2 piles, all the odds are facing up and all the evens are facing down. So when I split them, I'm really just separating out the different odd and even position cards, right? And now when Carolyn flipped one versus the other, they're all going to be facing the same way, right? So what we did is we had 8 put in this pile, 8 put in this pile, but when you flip, they either all become 1s or they all become 0s. So they're all facing the same direction, right? So that's what would happen if I didn't mess it up a little bit. So the key is, at this stage, I want all of the royal flush cards to be facing the opposite direction. Well, where did I decide what direction they were facing? I decided it when I first split them up into face up, face down, face up, face down, right? So what happens when I go through this, and again, it doesn't matter the order that I see them, what I do in my head, and there's all sorts of different styles for how you do this. Some people take cards 2 at a time and do a fancy flip thing with their fingers. But I'm not a magician, and I had to do it in a way that was a little bit easier. So what I do is I in my head, I say up, down, and if I come across a royal flush card, I do the opposite. So it's kind of like a pat your head, rub the belly type thing with those. So you do have to practice it. But what I do is I say up, down, but it's a royal flush, so I'm not going to turn it down. Up, down, up, it's a royal flush. Down, royal flush, so keep it. Up, down, up, down, up, down, up, down, up, and then down. Now, if you look, some are facing up and some are facing down, so this kind of disguises the fact that I've done some stuff with the royal flush cards, right? But if you look at it, the royal flush cards, this one should be facing down, right? It should be down, up, down, up, down, up, down, up, down, up, down. The ones that are mixing the pattern up are the royal flush cards, right? So in these, so I actually have it the backwards order, but I'm going to start from here. So I have my king of clubs. That's my first card. It's facing up. I've got this guy right here. This spade is facing up. I'm going to put a bar over it. It's actually facing up, but it should be facing down. My next card is a king of diamonds, facing up. Then this one faces down. Then the next one faces down because it is a queen of spades. So this one should be down, but that's a queen of spades. And then I am going up. Let's see. This one should be down.
No, next one.
Let's see. Let me count. So
0.
up, down, up, down, up, down. Yeah, this one should be down, but it's actually facing up. And then I've got up, down, up. So that one is, that was this one, I believe. No, it was this one. Here we go. Down, up, down. That is a 0. Up, down, up, down, up, down. So these cards right here are the royal flush cards. So I've marked them, I've identified them by having them break the pattern of my parity. So now what happens is when I separate them out, so this one goes here, this one, this guy is going the wrong direction with its mates, right? This one is right here, this one is here, This one is here, but it's actually facing the other direction. This one is over here, and it's a 1. And then I've got a 1, a 0, a 0, which I believe is this guy, a 0, a 1 over here, a 1, a 0, a 1, and a 0, right? So then, when I flip them, right, these are going to be 0, 0, 1, 0, 1, 1, 0, 0, 0, right? So let's say that Carolyn decided to flip this one over. So I would have 0, 0, 1, 0, 1, 0, 0, 0, and that would be on top of this, which is a 1, 0, 1, 0, 0, 1, 0, 0. And the 5 that are facing the opposite way are the royal flush cards. Yeah, so let's see how it would look here. So notice the only ones that are face up over here are going to be the royal flushes. And the ones that are facing down here are going to be the royal flushes. Yeah, so then when we flip, we have that. Yeah? So what's kind of deceiving is the fact that we can choose which cards we're flipping and not, but in fact we see that that doesn't really change anything at all because we're still preserving the parity. All right, so that's the Royal Hummer. I like that trick. I think it's kind of fun. So, and it's not that hard. Thank you. It's not that hard to do, right? It's a pretty basic trick, and you could do it with like all aces if you wanted to, or you could do it with all red cards and have the rest be black. So you can mix it up a little bit. And the Baby Hummer is just a smaller version of that. So if you want to pick up your cards, I'll have you do it again, and we can think about what's going on. So when you start, we've got all zeros, right? Because they're all facing down. But I have you look at the bottom card. So this is the card that we're going to be interested in. Now, the next thing that you do, so I'm going to put a star next to it. The next thing you do is you take the top card and you put it on the bottom. So it moves it over here. So now the card we're interested in is in the third spot. And the last step is to take the first card and flip it, which turns it into a 1 because it's face up. So notice that these are in the odd position. They should be facing up, but the way I told you to arrange your cards marks this as opposite of what it should be, right? So this should be facing up, but in fact it's facing down. So in doing that, we marked these two and we put them together. Now, when you cut, you're just taking some of these and moving them to the other side, but notice like if I cut here and I put these here, this is still matched up with the 1. If I cut here and I move the 1 here, it's still matched up with the 1. So since I have an even number of cards, anywhere where I cut, if I move them over here, these two are still connected to each other. And then when you do the flip, so let's say you flip, then this is going to become a 1 here and this will become a 0 here. So even though this particular card and this particular card might not be matched up anymore, this card is still matched up with the one that's facing in the wrong direction. So that's what's going on with the Baby Hummer. So it's kind of a smaller version of the Royal Hummer. Okay, ready for the next trick? This one, I believe, is called Coloria, spelled like this. Although there's a lot of variations on it, and I think this is an older name, so I'm not quite sure if this is actually the one we're using or not. But we're going to use not quite a whole deck, so I'll show you the cards I have. So we've got these. And I need 5 people. So maybe would you guys mind being my volunteers, and then Betsy also? You don't have to get up. Okay. So what I'm going to do is I am going to pass this deck to Brian, and he is going to cut once. So cut once. Okay, so then put the next one on top.
Just on top?
Yep.
Okay.
And then pass it to Kirk. Okay, cut once. All right, pass it to Rachel. Rachel's going to cut once. All right, and you are? Kyle. Kyle's going to cut once. Good, and then I'm going to give it to Betsy, and Betsy's going to cut it once. All right, now hang on to it.
Okay.
And Betsy's going to take the top card. Don't show me. Take the top card off. Hang on to it. All right. Kyle, take the top card off and hang on to it. And now pass to Rachel. Rachel's going to take the top card. Back to Kurt. And back to Brian. Good. Okay. So they've got 5 cards. And I'm going to tell them which cards they have. But I need a little bit of help, so I need to know which of you have a red card. So if you have a red card, raise your hand. So just these 2 have red cards? Okay, why don't you hold your cards up so that everyone else can see, but don't let me look at it. All right, so let's see. The first card is going to be an 8 of hearts. Is that true? So Betsy's got an 8 of hearts. The next card is going to be an ace. It's going to be an ace of diamonds. The next card is going to be a 3 of clubs. And then we're going to have a 6 of clubs and we're going to have a spade, and it's going to be a 5. Did I get it? Okay, all right. Okay, so let me. Okay. Let's do it one more time. So I need 5 more volunteers. How about these 5? Does that work?
Nancy cheats.
Okay, so do you remember what you do? You cut once and then pass it. So Jeremy, cut once. There you go. Pass it to Nancy. Okay, just 5. Just 5. Just 5. Yep, just 5. So take top card. Take it off. Yep, pass it back. Okay, all right. So which of you have a red card? 2 only. Okay, so I'm going to turn my back, and I'm going to have you guys show everyone else what cards you have. Okay, do you have it? All right. So the first card is going to be a 5 of clubs. Then we'll have a spade, a 3 of spades. And then a 6 of diamonds. And then another spade, a 4 of spades. And then the last one is the ace of hearts. Do we get it? All right. Okay, so got the cards back. Thank you. Okay, so let's see. All right. How does this work? In order for me to tell you how it works, I have to teach you a little bit of math first, which is why we're here anyway, right? This trick works using something called de Bruijn sequences. So let's see. De Bruijn sequences, the spelling, oh, I'll move this so you don't have to look at it. The spelling is like this. And I wasn't sure how to pronounce this, but I looked online and it seems like the consensus is that it's brown. Yes, yeah, it's Dutch. It's Dutch. So de Bruijn sequences of window length k are binary sequences. So binary, what does binary mean? It's in ones and zeros. Yeah, so we're only using ones and zeros. So it's a binary sequence of length 2 to the k. And if you look at all of the k consecutive digits, so if you take out k consecutive digits, each possibility occurs exactly once. So let me get the wording right for this. So such that every k consecutive digits appears exactly once, and you cycle from the end to the beginning. So I'll tell you what this means in a second. Okay, so this is the idea. We're going to look at the example where we have a de Bruijn sequence of window length k. So I'm going to take numbers or binary sequences where I'm only using ones and threes, and they're going to be length 3, or ones and zeros, length 3. So one example of this would be like 1, 0, 1. So this is a binary sequence of length 3. So can we come up with the rest of them? What's another one? What else could we have? 1, 1, 0, good. What else? 0, 1, 1. 0, 1, 0.
1, 1, 1.
1, 1, 1. And I think we got 2 more. 1 more?
0, 0.
Good. How many should we have? We should have 8. So for those of you who have done some counting, this is going to be 2 to the 3rd power. So there's 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 ways of arranging 2 numbers in 3 spots. So a de Bruijn sequence is going to be a sequence of length 8. And each of these arrangements of numbers is going to appear exactly once. So this is an example of one. So this is a de Bruijn sequence. So let's see if we can find our strings here. So I've got 1, 0, 1. This is what I mean by cycle from the end to the beginning. So when I get to the end, I cycle around. So I've got 1, 0, 1. That appears in here. I've got 1, 1, 0 right here. I've got 0, 1, 1. I've got 0, 1, 0 here at the end. We've got 1, 1, 1, 0, 0, 0, 0, 0, 1, and 1, 0, 0. So this is the shortest sequence that we can come up with that has all 8 of these strings in them. So this is what a de Bruijn sequence is. Now, you can find other de Bruijn sequences for window length 3, but for the most part, it's just like you could take the 0 and the 1 and tack it onto the end. So you could just kind of shift where you start, or you could go in the opposite direction. So for the most part, they're all related to each other. Now, how do I figure out what this sequence is? There's 2 methods of finding a de Bruijn sequence. One of them is to use a graph. How many of you know something about graph theory? Okay, if you don't, no problem. This is a really easy graph. I'm going to have vertices that match k minus 1 digits. So k in this case is going to be 3. So when k equals 3, for the graph, I'm going to take all of the binary numbers of length 2. So there's 4 of them. There is 0, 0. There's 0, 1. There's 1, 1, and then there's 1, 0. So I'm going to go to all the strings that are 1 less than what I'm looking for. And then I'm going to make a directed graph. So what that means is I'm going to draw a line from one vertex to another if the last digit here matches with the first digit of the vertex. So for example, this ends in 0, so I'm going to draw a directed edge, so from here to here, to this guy. What else can I draw this to? One other one. Yeah, straight across right here. Good, and that's it, right? This one isn't going to work. Okay, what about from 0, 1? So which ones start with 1? This one, right? So I'm going to draw a directed edge here. And then I can do one over here. Okay, this guy, so what ones start with 0? 0, 1. Now, actually, this also starts with 0. So the ending and the beginning are the same, so actually I'm going to draw a directed edge to itself. So I've got a loop in there. So the only vertex we have left is this guy. So which ones start with a 1? That's this one. And then what else do we want to do? Put a loop to itself, right? Good. This is called the de Bruijn graph for k equals 3. Now what you can do to find a de Bruijn sequence once you have the graph is you can just start at an edge and you can trace what's called an Euler circuit. So you want to make sure that you hit all of your edges. So I'm going to start, let's see, I'll start right here at 0, 1. And every time I go to a new vertex, I'm just going to add the number at the end of that vertex. So I'm going to start with 0, 1. And I have two options. I can either go here or I can go here. Yeah? Does anyone have a preference? Okay, 1, 1, 0. This is what the department head says, so I better do it. So 0, 1, 0. I'm going to add that at the end. Now my options are to either go back to 0, 1, or I can go up here. Let's go up here. And I'm going to add a 0. Now, I can either go around or I can go this way, but I want to get all the edges, so I want to go around because otherwise there's no way I can get back and cover this. So I'm going to go around now, which means I got to add another 0. And then I'm going to come over here and I'll get a 1. And then my only other option is to go this way and get a 1. And then I have to loop around in order to get this, so I'm going to throw another 1 in there, and then a 0. And then I'm going to end with a 1, and I've gotten everything. Now notice that this isn't length 8. What length is this? 10. But what happened here? Same thing, right? So actually I can take these off either from the beginning or the end. And I came up with the de Bruijn sequence. It looks a little bit different than that, but you'll notice that I think it's just, if I move this 0 here, it's backwards. So it's really related. So this is a de Bruijn sequence of length 3. In order to do this trick, we need a de Bruijn sequence of length 5. Now there's another way, I guess I should tell you this first. There's another way of coming up with the de Bruijn sequence, which is to use something called a linear shift register. Has anyone heard of linear shift registers before? Okay, it's used a lot in computer science. So for a linear shift register, I just start with one of my lengths of 3 bits. And then for this, I'm going to take the first digit back and the third digit back, and I'm going to add them mod 2. So what that means is that if I take 0 plus 0, what do I get? 0, and I'm going to add that, and then I'm going to shift over. If I add these, what's 0 plus 1? 1. Okay, 0 plus 1? 1. 0 plus 1? 1. Now, what's 1 plus 1? 2, but I'm in mod 2, so I'm going to say that that's 0. So what that means is anytime I get an even number, I just do 0. Anytime I get an odd number, I do 1. So 1 plus 1 is technically 0 in this case, right? And then I can keep going, but 1, 2, 3, 4, 5, 6, 7, 8. So I can stop there. So I have my de Bruijn sequence this way. So this, we used a linear shift register. To do it, and it came from adding these two. So add, and we get the next one, and then we shift down. So add first digit back and third digit back. That's the other way of coming up with it. If I do this for window length K, or 5, which is what we need for this trick, this is what the de Bruijn graph looks like. So it's big. So making the graph is not necessarily the most efficient way of doing this. Imagine if you had K equals 6. How many, out of curiosity, how many vertices do you think I have here? 16. Why 16? Okay. It's 2 to the 4th. So these are all of the possible ways of writing in binary 4 digits, which is 2 to the 4th, which is 16, right? How many edges are we going to have? You're going to multiply by 2 and get 32. So there's actually 32 different strings. So there's 32 edges that we have here. Now, we could go through this. For the sake of time, I'm not going to go through it, but I could pick a point and I could trace and go around and come up with the de Bruijn sequence of length. Window length 5, which would give me a 32 length sequence. But what I'm going to do is use the linear shift method to do this for K equals 5, because it's actually a lot faster to do it with the linear shift method than it is to do it with the graph, especially if you don't have the graph yet. So let's see. We had 5 of clubs. Okay, so we're going to do. So linear shift, you just start with a length 5 or length K binary sequence. And then I'm going to take, for 5, I'm going to take the 3rd digit back and the 5th digit back. So 3rd and 5th. And I'm going to add them. And then I'm going to put that number here. So 0 plus 1, so this gives me 1. So everyone tell me what I'm going to get. So this would be
0, 0, 1,
0. Have I hit 32 numbers yet? I'm going to keep going. Okay. Is that 32? Let's see. 1, 2, 3, 4, 5, 6, 12, 13, 14. 31. I need one more. So if I go 3 digits back. Okay. This is a de Bruijn sequence of window length 5. You have to make sure there's 2 to the 5th things in it. So if you were to pick any 5-digit binary number, you'd be able to pick it out in here somewhere. And there's only one of them. It only exists in one spot. What does this have to do with the trick? Well, what I'm going to do is I'm going to take any 5-digit string, which only appears once, so I'm going to look at this first one, and the first 2 digits are going to correspond to the suit. So if I have 0, 0, and this, if anyone plays bridge, this kind of follows the hierarchy of suits. So it's a club if it's 0, 0. It's a spade if it's 0, 1. 1, 0 is a diamond. 1, 1 is a heart. So notice that the red cards start with 1 and the black cards start with 0 right there. And then the last 3 digits in binary are going to give me the number of the card that I'm talking about. So in binary, this is 2 to the 0, this is 2 to the 1st, and this is 2 to the 4th. So if I have a 1 here, I've got 1, nothing here. This is, sorry, 2 to the 2nd, thank you. 2 to the 2nd is 4. So what card is this? It's a 5 of clubs. So these 3 numbers give me the card number, and this gives me the suit. if I have a 0, 0, 0, that's going to correspond to an 8. So that corresponds to an 8. So I can come up with 32 cards based on the string. So if you were to count the cards that I gave you, there's actually 31 of them. I'll tell you why in a second. But what happens is that when you tell me the colors that you have, so the last one we had 2 blacks, right? 2 blacks, a red, a black, and a red. 2 blacks, a red, a black, and a red. So from this, I just used the linear shift register. So what I did is I just quickly added to get these, and then I shift down. So this is a club, and it's a 5. This is a diamond, and it's a 3, right? Because this is a 2 and a 1. And then I shift down again. Oh, no, that was a spade, wasn't it? Yeah, that's a spade. This is a diamond, and it's a 6. So I've got 4 and 2. This one right here is a spade, and it's a 4. And then I shift over again. This is a heart, and it's an ace. And then I could keep going. We could keep going after that. Are there any questions about how you interpret the number to be a card? Yeah.
Why is it, I don't really know much about binary. How does the 1 become 2 to the second? How does that work?
So this is telling me that I have 2 to the 0, which is 1. And this is telling me that I don't have any 2 to the first powers. And this is saying I do have a 2 to the second. So in fact, any number, any natural number can be written as a power of 2's. So 9, for example, you could write that as 2 to the second, 2 to the third, plus 2 to the 0, which would be 8 plus 1. So this is how I was able to match the cards that you gave me. This told me where to start. It told me where I was in the sequence. So if you had told me that we've got a red, a black, a red, and a black, where would that be? So 2 reds, a black, a red, and a black. Right here? Yeah? So I can find the spot in the sequence. I just use the linear shift to come up with the next couple digits.
So you already had this whole sequence written out?
Yes, so the cards I gave you were not just any cards. They were in an order. They don't look like they're in a particular order, which is why it's okay if I show you these, right? Because it doesn't look like it's in any particular order at all. But in fact, they're in a de Bruijn sequence, organized in a de Bruijn sequence. Now, you may have noticed that in this de Bruijn sequence, I don't have an 8 of clubs. What would an 8 of clubs look like? What's the 5-bit sequence that matches 8 of clubs? 5 zeros. What would happen if I had 5 zeros somewhere in the sequence? The linear shift is just going to give me 0, 0, 0, 0, 0, right? So I can't have that in there because it's gonna mess it up. So if I do a de Bruijn sequence using the linear shift, it's actually 2k minus 1, and then we've got the 0, 0, 0, 0, 0 left out. Now, if you're trying to come up with a de Bruijn sequence, it's not too hard to make a true one by, so I really want 31. I just put a 0 somewhere in my 4 string. And that'll take care of it. So over here, let me point out that with the linear shift, we really would want to do 7, like that. So this wasn't a true de Bruijn sequence, but I will point out now that what I would do is I'd plug a 0 in here, and that would give me the true de Bruijn sequence. Okay. An application of this is not just magic tricks. This is used if you use 2-dimensional versions of these. So you can have a grid like this and fill it with 1s and 0s in such a way, we'll make it square, in such a way that if you take like a 2x2 square, you have a unique arrangement of 0s and 1s. So this would be different than this. So you can arrange things in a way that you can have this 2-dimensional mapping where if you look down and see exactly what's underneath you, you know exactly where you are on the grid. This they use for robots. For robots to tell where they are, they give them a grid, and then like if a robot wants to know where it is, it can read the location that it's standing, and then it can determine where it is in relation to some grid that's been determined. Apparently these are also used with the pens. If you have those smart pens where you use the special paper and you write with the pen and then it can translate it into your computer, it does the same thing. So the pen is able to read where on the page it is using a de Bruijn sequencing like this, and then it can feed the information back so that you can get a true arrangement of what you were writing. So I think that's kind of a cool thing. I guess it's used in DNA sequencing as well. Now, there's a natural question that arises from this. I'm wondering if anyone else has come up with this question about the de Bruijn sequences and the linear shift. Why are we doing the 3rd digit back and the 5th digit back? What if we did like the 4th digit back and the 5th digit back? Would that work? This is what I was wondering, and it turns out that it matters. We can't just use any 2 digits and add them. We have to use a couple specific digits. So the ones that we can use, and this is going to get into some stuff that unless you've had group theory, you might get a little, don't get overwhelmed. So I'm going to show you something. These are the primitive polynomials. And I don't fully understand these. This is kind of what I'm trying to figure out myself. So the idea is that if you have a k value, so in this case I've got a k value of 5, if you take 2 to the k power, which is 2 to the 5th, which is 32, if you take the polynomial x to the 32, I believe it's minus 1, if you look at all of the polynomials of power 5, of degree 5, that evenly divide this. So if you've taken algebra, you know how to do division of polynomials. So all of the polynomials of degree 5 that evenly divide this are right here. They're these ones. This might be a +1. I don't have to check, but it's one of the two. Those are called the primitive polynomials. Now, if you've taken algebra, you know what it means. If a polynomial divides another, they have the same, what? They have a root in common, right? So the roots of this would be the same as the roots of x to the 32 minus 1. So we can use this to figure out which digits we can use. So look at this guy right here. This is one of the primitive polynomials for k equals 5. It's got a x to the 5th and an x to the 3rd. So that's telling me I can go 3 digits back and 5 digits back and add those, and I'll be able to generate a de Bruijn sequence. I could also go 2 digits back and 5 digits back and add those. So I could, instead of adding the 0 and the 1, I could add 0 and then that 3rd 0. So I could do that, and that would also generate a de Bruijn sequence. I could also add the 1st, 2nd, 3rd, and 5th digits back, and that would generate a de Bruijn sequence. So I can't just add any combination, but if I follow the primitive polynomials, I can generate a de Bruijn sequence. This is what I don't really know about. I'm not sure how that works. I found a paper that talks about it that I'm reading through, but it has something to do with Galois fields, mod 2. And if you know anything about Galois fields, that has to do with like finding the roots of polynomials. So there's something about the fact that all these primitive polynomials have roots in common with this that make it work, so we get this sequence and we're generating exactly what we need. I don't know how it works yet, but I think it's a pretty cool problem. And if anyone wanted to learn more about groups, I think it would be a neat problem to work on. Even if you don't know about groups, this paper that I have outlines it pretty well. So, and I'll show you the paper. So this is the name of the paper. So a fast identification method, that's kind of talking about the de Bruijn sequences. So I have it up here if anyone wants to look at it. But I found this quote online from, I think it was the Wolfram site. So they said, amazingly primitive polynomials over GF2, so that's the Galois field mod 2, define a recurrence relation which can be used to obtain a new pseudo-random bit, which are these length 5 bits, from the n preceding ones. So the idea is these primitive polynomials can be really useful in creating these de Bruijn sequences. All right, that is my talk, but I can answer questions if you have any questions. Yeah.
When did we figure this stuff out? When did this happen?
That's a good question. Let's see if they say in here. I'm not seeing, well, in the 1960s, they were working on the tricks. So before the 1960s. But I don't see a date, but I wouldn't be surprised if it has it in here. Yeah, if you want to. The authors, so Diaconis and Graham. So Percy Diaconis and Ron Graham are the authors of this book. So if you read the abstract, they're the ones who wrote this book, and they worked on the magic trick. Yeah.
So they were trying to develop the tricks that author of this book?
Yes, yeah. So they were using this to come up with different magic tricks. Yeah. Yep. Yes.
Does this tie in closely with the development of early computer programming?
I wouldn't be surprised. I know the linear shift registers are used a lot in computer programming. Yeah. Yeah, and the key is that it's a really great way of determining a location within a sequence. Yeah. Mm-hmm.
What were the authors of that book again?
Diaconis and Graham. Here, I'll give you this. Let me write it up in case anyone wants to see. Yes.
So you don't think these tricks existed prior to the 60s?
I think versions of them did, but maybe not in this form. And in the book, they say a lot like, we invite you to make new tricks based on this, and if you come up with one, let me know. They did a two-dimensional one they did a seminar at Harvard with a bunch of mathematicians, and they asked them to come up with a new trick. And what they came up with was they had a map with countries that are squares, and they colored the squares based on whether it was a hot country or a cold country. And they used a cross sign like this. So you can take this and put it over your map, and then you can just ask them like whether you have a hot country or a cold country around it. So you don't ask about the one that you're on, but you ask about these, and you can find your location based on what these are with the de Bruijn sequence. And then you can do kind of like a three-dimensional version of this. So that's what the Harvard math folks came up with. That was their magic trick.
So you think the tricks were driven by the math, and that the math wasn't driven by the desire to figure out why the tricks work?
Yeah, I think there's kind of a lot of back and forth. And they talked a lot about the DNA sequencing here, and they said that this was something that came out of the de Bruijn sequencing, and then in turn that kind of, however they use it for the DNA sequencing, then you can use that for a magic trick, and then maybe in the magic trick you might change it around, and then maybe that applies to something else. So there's a lot of back and forth, which is kind of cool. Any other questions? Yeah.
Do we know why de Bruijn eventually came up with this? First came up with this?
I am not sure. I'm not sure. Maybe out of curiosity. Yeah.
What led you to this?
Well, someone gave me the book, and then this summer I was sitting around reading it, and these were the tricks that stood out that I thought were kind of interesting. Yeah. Increase. Yeah. Yeah. And I don't really know that much about about gray code and sequencing and all that. So I thought it was kind of a neat way of learning more about it. I hadn't even used binary that much before. Yeah. The book is here if you want to take a look at it, and I also have the paper too if anyone is interested in the algebra behind it. And thank you for coming.
Thanks.